Good evening, everyone. We'll just start in a minute. I'll just plug in the charger and we'll start. So, meanwhile, can you tell if my screen is visible and am I audible? Yeah. So, can anyone please give a thumbs up if you are able to hear me and you are able to see my screen? We'll just start. Yeah. Thanks, Nisha. Yeah, so we'll start. Welcome again to this NPTEL problem solving session for week 3. So, in this week, you went through MOSFET characteristics. You studied about its static characteristics and dynamic characteristics. I guess you would have gone through its switching process as well. You would have learned about the switching transitions during turn on and turn off, right? Using the MOSFET capacitances, those are explained. And then you also learned about one particular characteristic, that is about the reverse conduction of MOSFET, which is possible through its body diode or anti-parallel body diode as we call it. We also studied about transconductance and how the MOSFET kind of operates as a switch in the cutoff region and the ohmic region, and it operates as an amplifier in its active region, right? And you also learned that when a switch turns on or turns off, it transitions from cutoff region to ohmic region or vice versa, going through the active region, right? So in the active region, you do know that your if your VDS, right, if your VDS is more than VGS minus V threshold, you tell that it's in the active region, right? And if VDS is less than VGS minus V threshold, only then you call it to be in the ohmic region. So if it's in the ohmic region, obviously you can kind of approximate your MOSFET to be a resistor, and you call this as RDS on, right? Drain to source resistance in its on state. And you of course know this is actually a variable, right? Because it depends on multiple parameters, including the junction temperature of the device and of course the channel current. Okay. So this is in the active region. So this is if the device is in the active region, and on the other hand, if your device is I'm sorry, if your device is in the ohmic region. On the other hand, if your device is in the active region, you so this is ohmic. So on the other hand, if your device is in the active region, you approximate it as a voltage controlled current source, right? So this is a VCCS, that is a voltage controlled current source. Why? This is a current source, which means that it is going to be I channel or IDS as you can call it for now. So I channel will be a function of your transconductance into VGS minus VTH square, right? So this factor is something that researchers have worked on. So people have also approximated it as simply GM into VGS minus VTH without including the square part. But okay, for now we can approximate that it's power 2. So we call it a voltage control current source. The reason being that I channel is being controlled by VGS, right? That is the gate source voltage. So if you control the profile of gate source voltage, if you control VDS, if you control VGS, that is the gate source voltage, you control I channel, right? You control I channel. So that's why we call it as a voltage controlled current source. But of course, you know that if it is in the voltage control, if it's acting as a voltage controlled current source, or if it is in the active region, you know that your VDS is pretty high, right? So the power loss across the device or the power dissipation across the device is going to be VDS, which is a fairly high quantity multiplied by each channel, and this is going to be something that's really high. Whereas on the other hand, if your device is in the ohmic region, you understand that your um, power loss will be simply I channel RMS square into RDS on, right? Your RDS on will be of the order of a few milliohms, few tens of milliohms, okay? So since it is in milliohms, the power would be low, power loss would be lower. So that is why we prefer always to operate the MOSFET in its ohmic region and not in its active region, right? Okay, so this is something I think which you guys are aware of already. Of course, you know that if it's in the cutoff region, it acts as an open circuit, right? Okay, so you went through as to how to read a MOSFET data sheet, right? And then you came to IGBTs, you studied about its characteristics, right? So IGBT is kind of a hybrid between a BJT and a MOSFET. You of course know that it's an insulated gate bipolar transistor. So therefore, you have gate characteristics similar to that of a MOSFET. However, the conduction is through the power BJT, right? So IGBT is of course, you learned about IGBT after learning BJTs and MOSFETs, right? So today we will move ahead with the problem solving session, and as usual we have a mix of theoretical and numerical questions. So wherever possible, we can solve it on screen over here, and some of the problems I'll just show the solution and go through the process in the interest of time. Okay. And of course, at any point of time, if you have any doubt, you are welcome to ask it or post it in the chat box, and I will check it. Um, I will check it often. Okay. Okay. Right. So this is a pretty simple question. In the case of high voltage applications, we use dash, and in case of high frequency applications, we prefer dash. So since in this week you learned about both devices that answer this question, I think you can answer. For high voltage applications, we prefer IGBTs, and for high frequency applications, we prefer MOSFETs. Okay. So yeah, option D. Okay. So why is this, right? So if we go through the internal structure of the device, you understand that MOSFET is a majority carrier device, right? So if you tell that it's going to be a majority carrier device, you understand that it can allow faster switching times, right? So you know that T on and T off, or in our case, let's call it TR, that is the rise time, and the T fall time, right? So in our case, the TR and TF are going to be very small. Okay. But point is, so you know that if your switching times are small, you can push towards higher frequencies. You can go for higher frequencies, right? So let's say you operate at 10 kilohertz, right? You operate at 10 kilohertz, which means that it is around 100 microseconds. It is the total switching period, right? So then let's say typically for MOSFETs that rise time and fall time will be of the order of a few tens of nanoseconds. So let's say the rise time and fall time are some 50 nanoseconds each, right? So 50 and 50 makes 100 nanoseconds is the total switching time, right? Or that is the time required for the device to turn on and turn off. Okay. So which means 100 nanoseconds is your switching time. So if your 100 nanoseconds is your switching time, you can very well operate at 100 kilohertz as well, right? Which is 10 microseconds. So 100 nanoseconds out of 10 microseconds is just 1%, and therefore you can easily go ahead, right? And even with newer devices, so in MOSFETs, typically you would have seen semiconductors that are made up of silicon, right? So silicon is one of the heavily used or widely used semiconductor devices. But however, for power applications, we have got sorry, for power applications, we have got MOSFETs that are manufactured of silicon, and recently we have got devices that are made up of gallium nitride and silicon carbide as well. So the advantage with silicon carbide and gallium nitride is that they allow for higher switching speeds. Okay, so higher, or I should not write it higher, it should be faster, right? So it should be, they allow faster TR and TF. So whatever we saw as 100 nanoseconds can be halved or even be made lesser. Okay, so they can be made to around 40 to 50 nanoseconds. So if you tell that your TR and TF are just 40 to 50 nanoseconds, obviously you can go for even higher frequencies, right? Even higher switching frequencies. Even higher switching frequency. So people have been able to operate silicon carbide devices typically to, typically till around 100 to 250 kilohertz or so, right? And with gallium nitride, people have been able to go till megahertz level. One of the widely used applications is something called as capacitive wireless power transfer, wherein the wireless power transfer happens to through parasitic capacitances that are formed between two plates. So in that case, people have been able to go till 6.78 megahertz, right? So you understand that if it's around 6.78 megahertz, the switching time itself is of the order of few nanoseconds, right? Right? So we will be able to go till this much high frequencies only because your TR and TF are lesser, right? In this case, it can be made even till less than 10 nanoseconds. So this is an advantage that you get with majority carrier devices. Okay. So MOSFET is a majority carrier device, enables you to go towards higher switching frequencies. Okay. So this is one of the advantages, but on the downside, if it is a majority carrier device, you have a higher resistance. So you have something called as RDS on, right? So you understand that as you push more and more current, you are able to get more and more losses, right? So P is I square R, right? So if you push more and more current, you are going to get more and more losses. So this is a limiting factor towards use of MOSFETs for, for higher power applications. So you can use MOSFETs for high frequency applications, but you are not, it is not a viable option to use MOSFETs for higher power applications. Why? Because it's going to be I square R loss that happens across the MOSFET, and you know that as you go towards higher and higher power, your I will increase, and since your current is going to increase, your I square R losses are also going to increase, right? It will be a square, correct? I mean, it's a square relationship. Okay, so this answers why we prefer MOSFETs for high frequency applications and not for not for high power applications. But what about IGBTs? IGBT, as you might have understood, it's, it is controlled by MOSFETs for as far as the gate side is concerned. So you do have what are the what do you generally have in MOSFETs such as CGS, CGD, and CDS. Similarly, you have CGE over here as well, and that is what you are going to charge up and discharge every time you turn on and turn off the IGBT. However, the main conduction happens through the BJT process, right? So you have what is known as this conductivity modulation, and IGBT is of course a minority carrier device. So one of the characteristic features of minority carrier devices is that they are very slow in switching. Okay, so your TR and TF are going to be small, or I'm sorry, they are going to be pretty large. TR and TF are large, therefore you cannot go towards higher switching frequencies. Your switching frequency will be lesser. But on the upside, what you get is that your on resistance will also be lesser. So there is always a fixed drop that occurs. Okay. So it's not going to be a square relationship. Okay. So you always get a VCE drop across the device, and that is actually going to um, be a bulk of your losses, right? So since the loss would now be VCE multiplied by I, it is no longer a square relationship, it's just a linear relationship. Therefore, you can push more and more power. Okay, so this answers why IGBT can be used for higher power applications and MOSFET is used for high frequency applications. Okay. Yeah, so as I was telling, so it shows both the static curves over here. From this itself, you can understand in the majority carrier device or the MOSFET, the R loss is I square R, I square into R on, and R on is actually your slope across the slope in your VA characteristic, right? So slope actually gives you delta I by delta V, or 1 by slope will give you your R on. Okay. Whereas in minority devices such as diodes or IGBTs, you understand that there is always going to be a fixed loss. Okay. So fixed loss VCE. So your power loss will be essentially VCE multiplied by the collector current, that is IC. Okay. So since it is not a proportional relationship, I mean it's not a square relationship, you can go for higher and higher power. Okay. So we'll go to the next question. Switching times of a MOSFET essentially depends on dash frequency of the supply, charging and discharging rate of the parasitic capacitors, charging and discharging rate of parasitic inductors, power voltage current of the given system. Okay. So you understand that the internal, even though we represent a MOSFET, right? So we represent a MOSFET in channel enhancement mode MOSFET. So that is what we typically use in power applications. We represent a power MOSFET something like this, okay? Wherein your this terminal is your drain, this terminal is your source, this is your gate, right? So, and this represents the anti-parallel body diode. Okay, BD is the body diode. Okay, so this is the representation of a MOSFET, but if you actually see the internal structure, you will know that it is composed of a lot of parasitic capacitances. Essentially, 3 parasitic capacitances. Okay, so you can understand that in order to charge a capacitor and discharge the capacitor, it takes time, right? For example, if you have an RC circuit over here, right? So let's say this is some 10 volts and you have a particular R and particular C. So you tell that the voltage across the capacitor is going to be something like 10 multiplied by 1 minus e power minus t by tau, where tau is equal to RC, right? So you understand that eventually in steady state, the voltage across the capacitor will reach 10 volt. But point is, the graph would be something like this, right? It would reach 10 volt after a very long time. And what about this profile? This profile depends on the value of your R and C that you are having over here. So essentially, if you control your R, you control whether your graph is going to be something like this, or whether it will be something like this, or whether it would be even faster. Right? Okay. So it depends on the value of R. Lesser the R you put, faster would be the capacitor charging. So you understand that essentially, if you see the internal structure of the device, right? So the device would be composed of 3 parasitic capacitance, as we mentioned, that is CGS, CGD, and ZDS across the gate source, gate drain, and drain source. Okay. So when you tell that you are turning on and turning off the MOSFET, you are actually charging and discharging these capacitances. Okay. So what we will be having in a typical circuit would be, if I can complete the circuit, it would be something like this, right? So your drain will be connected to some other part of the circuit, and your source would then be connected to some other part of the circuit, or let's say it is connected to ground for now. Okay. So your drain will be connected to some other part of the circuit. So what you will be having is essentially, you will be having a gate resistor over here that you will put externally, okay, and you will be feeding it the gate supply, okay. So this gate supply may be 15 volts, okay. So it is not essentially a DC supply, it would be a square wave-ish supply, right? Because you would be having something like this, and it will vary from 0 to 15 volts, let's say for now, right? So 0, 15. You understand that when you want the MOSFET to be turned on, you apply 15 volts over here, and when you want the MOSFET to be turned off, you apply a 0. So what will happen is once you apply 15 volt, the CGS capacitance, let's assume it was initially uncharged. So what will happen is VGS, right? VGS is the voltage across the CGS capacitance. So what will happen is essentially CGS voltage will slowly increase and then it reaches 15 volt. Okay. So we understand that it takes a certain amount of time for it to reach 15 volt. Okay. And prior to that, you of course know that if it's an in-channel enhancement mode MOSFET, your VGS is positive. So let's say your VGS was somewhere here. I mean, your VGS threshold is positive. Your threshold is positive. So let's say your threshold is somewhere here, right? So you understand that even though you gave a pulse at this instant, right? You gave or you fed in um, you fed a 15 volt pulse at this instant, right? You fed a 15 volt pulse at this instant, but the voltage across your CGS capacitance is increasing something like this. Why? Because it's an RC charging circuit, CGS cannot increase to 15 immediately, so it increases gradually or slowly, right? So we understand that it takes a finite amount of time to hit V threshold, and only after that your channel will start conducting. Okay, only after this point your channel will actually start conducting. Okay, and only after this point you will see that the current through the MOSFET will rise. Okay, only after this point you will see that the current will rise. So we call this period, okay, that is from the point at which the current starts rising, right, to the point at which the voltage falls to 0. We call this period essentially as the rise time. Okay, so you understand that there is a finite rise time, and why is it happening? Because you have an RC charging circuit over here. So essentially the slope or that value of TR actually depends on what value of RG and C you have over here. So by controlling your RG or C, you can control the switching speed, right? Similarly, the same thing applies when the capacitor turns off as well. So when the capacitor turns off, it will of course not come to 0 directly. It will slowly come to 0. Okay. So to answer the question, the switching time of a MOSFET essentially depends on the charging and discharging rate of the parasitic capacitors. Okay. I think you would have gone through a detailed explanation of what happens during the switching period in the lecture slides as well. But just for you guys to remember, there are these three parasitic capacitances, and hence, when you have an external RG, you cannot instantaneously, obviously, charge up the CGS. It takes a finite amount of time to charge up. And of course, there will be a current that flows over here, which will gradually decay to 0. Okay. For the power semiconductor devices, IGBT, MOSFET, diode, and thyristor, which of the following statements is true? All four are majority carrier devices? No. Why? Because IGBT is minority carrier device. MOSFET is majority carrier device. Diode is again a minority carrier device, and thyristor is of course a minority carrier device. Okay. So all four are minority carrier devices? No and no. IGBT and MOSFET are majority carrier devices. Diode and thyristor are minority carrier devices? No. MOSFET is a majority carrier device, and IGBT, diode, and thyristor are minority carrier devices. True. So option is B. This is a pretty simple question, I believe, right? So high frequency operation of any device is limited by what? Forward voltage rating, switching losses, thermal conductivity, or heat sink arrangement. Okay, so yeah. So high frequency operation is not limited by voltage rating, right? So a device may be rated for 50 volts or 500 volts. It may be that the 500 volt device is able to operate at 1 megahertz, whereas the 50 volts device is not able to operate even at 500 kilohertz. Okay. So forward voltage rating doesn't have any connection whatsoever to the high frequency operation capability. And how to compute them in the lecture slides as well. So how you compute the switching losses is basically you compute the switching energy, right? So first you compute the, I'm sorry, switching energy during turn on and turn off. And you would have studied that the formula is roughly given by 1 by 6 into V into I into TR plus TF, right? If you consider the on and off time. So this is the switching energy. And this would be obviously, since it is energy, it is in joules, right? So it is in joules. So to convert that into the power, so you understand that this much switching energy is expended, or it is used up every time the device turns on and turns off, right? So let's say the device turns on and turns off, turns on and turns off. So during these instances, right? So during these instances, there is a finite amount of switching energy that is involved, right? So you have studied in detail about that. That is your um, that is what happens. Okay, let me erase this. So what happens essentially is yeah. So you understand that I was talking about the overlap of voltage and current. So for example, let me call this as voltage and the blue one is the current. Okay. So you understand that during turn on and turn off, there is a definite or finite overlap between the voltage and current. Okay. So there is a finite overlap between the voltage and current. Therefore, some switching energy is expended every time. And how frequently does it happen? It happens every switching cycle, right? So it happens in every switching cycle. Okay. So the power or the switching loss or the switching power loss is given by your switching energy. I will call it as E into the frequency, right? Because energy by time is actually power, right? So or E by Ts I can call it. Okay. So you understand that as your Fs increases, or switching frequency increases, more and more power loss will happen. Okay, more and more power loss will happen as your Fs increases. Why? Because this is going to happen even more often, right? The turn on and turn off are going to happen more often. Okay, so that will result in unnecessary switching losses, or it will result in power loss. And you understand that the power loss is directly proportional to frequency, right? So you operate a device at 10 kilohertz and you operate a device at 100K, switching loss will be into 10. Okay, switching loss in the 100K case will be into 10. So high frequency operation of any device for that matter is limited by switching losses. Okay. So now you can tell that since it is getting restricted by switching loss, and switching loss can contribute to the overall losses of the device and result in heating up of the device, you can tell that heat sink arrangement is also impacted. Okay, because you are operating at higher switching frequency, it leads to higher switching losses. Because of that, there is heat generation in the junction of the device. Junction temperature increases. To limit that, we have to put elaborate heat sink requirement. Okay, so essentially it is switching loss, right? Okay, so this is something that we saw previously as well, and I have just jotted it down over here. IGBT and BJT both possess dash low on-state power loss, high on-state power loss, low switching loss, and high input impedance. So as I was telling, both IGBT and BJT are minority carrier devices. Okay, which means that the on-state loss is going to be a fixed drop across the collector to emitter, right? There will be a fixed VCE loss across the collector to emitter drop. So that multiplied by your collector current will be your on-state power loss. Okay. Whereas for majority carrier devices, you saw that the loss was I square R. Okay. So since this is a fixed VCE drop multiplied by just the IC current, the losses will be comparatively lesser in case of minority carrier devices compared to majority carrier devices. Why in majority carrier devices it's I square R? You cannot go towards higher and higher powers, but in IGBTs you can push for higher power. Why? This is because of low on-state power losses. Okay. Which of the following are true about MOSFET? It is a charge rate control device. That is it controlled by dQ by dt? Or is it controlled by Q? It's a charge control device. Um, it's a charge control device. It is a four-terminal device. Across gate source terminal, a negative voltage cannot be applied. It has an internal body diode. So which of the following is true is the question, right? So this is, I guess, a pretty simple question we need just to identify. So as we were mentioning earlier, the MOSFET essentially consists of parasitic capacitances, right? So it has CDS, it has CGD, and it has CGS. So you control the charge that is pumped into this device. You control the charge that gets pumped into this device or charge that is taken out of this device, right? So it is a charge control device. Okay. And is it a four terminal device? No, it has only three terminal device, three terminals, drain, source, and then gate. Okay, so it is not a four terminal device, it's not controlled by charge rate, right? And across gate source terminal, a negative voltage cannot be applied. So first of all, we will assume that we are talking about power MOSFETs, right? Just to avoid ambiguities. So power MOSFET means typically it is an N channel enhancement mode MOSFET. Enhancement MOSFET. Okay. So obviously your V threshold is positive. V threshold is positive. Okay. So across gate source terminal, a negative voltage cannot be applied. It's not true. You can apply a negative voltage, but point is the MOSFET won't turn on. So if it is about turn on, of course, a negative voltage will not turn on the MOSFET. Okay. So let me complete this sentence just to avoid ambiguity. A negative voltage cannot be applied to turn on MOSFET. Yes, it is true. Negative voltage will not turn on the MOSFET. You need a positive voltage to turn on the MOSFET. And it has an internal body diode as well. Right? So B, D. Okay. So D was kind of an ambiguous statement. So I just corrected it because it is not given about the nature of the MOSFET, whether it is internal enhancement or what they want to tell, whether to turn on or turn off the MOSFET. Okay. Whereas you would have studied about JFETs. So JFETs are normally on devices. Okay, so they are normally on, which means that you need to apply a negative voltage to turn off the device. Apply a negative VGS to turn off the device. Okay, so JFET is a normally on device, which means that so its threshold may be something like, let's say, for example, minus 1.5 volt. Okay, it will be minus 1.5 volt. Oh my God. Oh, something happened. I'm not sure. So as I was telling, JFET is a normally on device. So its threshold may be something like minus 1.5 volt. It means that you need to apply a voltage lesser than minus 1.5 volt to turn off the JFET. Turn off the JFET. That is, let's say your threshold is minus 1.5. You apply minus 3 volts, the JFET turns off. And you make it 0 volt, the JFET turns on. Okay, simple. So JFET is a normally on device, whereas MOSFET is a normally off device. If you assume that it's an N-channel enhancement mode MOSFET. Okay, fine. Okay, so we will step into numerical problems, but till this point, if you have any doubts, please do go ahead and ask, or else we will jump right ahead into that. Okay, so what negative voltage rule will be, sir? So the point is, it depends on the type of the device. So as I was telling, JFETs are normally on devices. When you tell that they are normally on, it means that when your gate source potential is 0 volts, right? It can conduct from drain to source. Okay. And if you want to actually turn off the device, or if you want to control the device, what you apply is you apply a sufficiently negative voltage to actually turn off the device. Okay. So as I was telling, if the threshold is minus 1.5 or minus, let's say minus 2 volt, then you tell that if the threshold is minus 2, I need to apply a voltage lesser than minus 2 volt to actually turn off the device. Okay. So yeah. Um, So I'll just take a pause over here for a minute. Yeah, and for MOSFETs, it is they are if you assume that they are power MOSFETs, which are in-channel enhancement mode MOSFETs, then in that case, yeah. So in that case, what happens is the threshold is positive, and therefore you need to apply a positive voltage to actually turn on the MOSFET, or else it is normally off. Yeah. So please give me a minute break. I'll just have some water and we will go into numerical problems. Okay. Yeah. So we will go back. Just a second. What about substrate? Oh, sorry, I didn't see this. What about the substrate terminal? Okay, so about the four terminal device you are asking, I guess. So what I mean by terminal is something that's accessible outside, right? That is, or in other statement I can make. So terminal is something that is part of your state variables. Okay. So what do you call as state variables? It can be your input parameters or your output parameters, right? So in this case, you have your gate terminal, source terminal, and drain terminal, which are accessible outside the device. Okay, in some devices, you have something called as a Kelvin source, but still it is internally shorted with the source. So the point is, you have only three terminals that are electrically available outside the device. Okay, substrate is something that's part of the die inside the MOSFET that you have, right? So substrate is just kind of so substrate is something on which the wafer is actually fabricated. So point is substrate is not essentially terminal. So terminal, what I mean over here is just the electrical connections that are available for me outside. Okay. Okay. So we can go back, I guess. So yeah, we will start with numerical problems. So a MOSFET IRF 840 is operating at 50 kilohertz switching frequency with a zero point 0.4 duty ratio. Okay, connected to a resistive load of RL equal to 20 ohms and a voltage source of VDD equal to 40 volt. VGS is 10 volt. Considering off-state power loss to be zero, find out the total power loss, including both switching and conduction losses across the MOSFET. So point is you just need to find the power loss, and they have given the operating switching frequency, the duty ratio, and the load and stuff is also given, right? The voltage source is also given, the VGS is given. So first things first, you need to construct the circuit. You understand that the MOSFET is connected with a load, right? So you just have a voltage source, you have a MOSFET, and then you have a resistive load. So based on that, you can draw the equivalent circuit. So you can understand that the circuit would look something like this, right? So you have your VDD that is given, RL is also given, and you have a MOSFET, and the VGS is also given, right? That is the gate source voltage is also given. So this is a circuit. So once you draw it, things become simpler, and I guess the answer is now easy to get. Okay. Okay. So more things are required, right? So point is, if you have to find out your switching loss, you require information about TR and TF. Okay. And if you require conduction loss, you require information about RDS on. Okay, so because these are device parameters, so that is why they have given the MOSFET part number. Since the part number is given, what you can do is you can actually go to the device data sheet, right? So IRF 840 is, so I guess my screen is visible, right? So IRF 840. So and go over here, you open the data sheet. Yeah. So in this data sheet itself, you can find out the required values. So you understand that your RDS on will be given over here. That is, yeah, at a VGS of 10 volt, the RDS on is 0.85, right? Or 850 milliohms. So you can see over here, it's highlighted in my cursor as well. RDS on is 0.85 ohms. Okay. So RDS on is 0.85. And then what about TR and TF? The switching times would be given probably over, yeah. So switching time, that is TR, is given as 23 nanoseconds and TF is 20 nanoseconds. Okay. So TR is 23, TF is 20. So one thing you need to observe, or it's an extra thing that I'm telling, is that see, TR and TF are actually given at a particular operating condition, right? 250 volt, 8 amperes, RG is 9.1 ohms, RD is 31 ohms. Okay, so you understand that TR and TF are given at a particular operating condition. So the values of TR and TF will actually change with the operating conditions. Okay. For now, we will not consider that. But if you go to perhaps master level courses, you will understand how to actually compute your TR and TF. This TR and TF that they have given over here, 23 and 20, they are actually experimental data at a particular operating point. Okay. See figure 10b they have told. So they have operated with this MOSFET experimentally and they are telling it's 23 and 20. But actually, based on your charges, right, based on the gate charge and all, you will be able to accurately compute what will be your TR and TF at a particular operating point. Okay, so let's say I change my RG from 9.1 to 12.1. Then your TR and TF will change. How will they change? How much they will change? You can actually compute theoretically. So that will be part of your master level courses, but for now we can consider TR and TF to be 23 and 20 respectively. Okay. So your TR is 23 nano, TF is 20 nano, and RDS is 0.85 ohms. Okay. So everything else is given. Just we need to find out the conduction loss and the switching loss. So what have they given extra? 50 kilohertz switching frequency with 0.4 duty ratio. So what is 50 kilohertz switching frequency? 50 kilohertz means TS, or the time will be 1 by 50k, right? That will be 20 microsecond. So how, and it's 0.4 duty ratio, meaning that your VGS will be something like this, where let's say this is 0, this will be TS or 20 microsecond, then this will be 0.4 times that, right? So sorry, so this will be 0.4 into 20 micro. Okay, right? So 20 into 4 by 10 or 8 microsecond. So this is totally 8 microsecond and this will be the rest 12 microsecond. So this is how your VGS is looking like, right? And you are supposed to find out conduction loss and switching loss. So switching loss happens during this interval and this interval, and conduction loss happens during this interval. They have given that the off-state loss is 0. Okay, fine. Yeah, so that is what we did. We used the RD ERF 840 data sheet. Okay, so first of all, what is RDS on? RDS on is 0.85 ohms. Okay, so we will go back over here. Right. So your VDD was given as 40 volt, and your RL is actually 20 ohms. Your RD is actually 0.85 ohm. Okay. So what is your current when the device is on? So I is equal to V by R, right? So 40 divided by 20 plus 0.85, right? Or 40 divided by 20.85. Okay. So this is your actual current when the device is on. So it will be good if you guys can also do it with me as I do. So if you have calculator and you can unmute and tell what is the actual value. Just give me a second, I will take my. Yeah. So So it will be roughly 1.918. So I is 1.918 amperes. So when is this flowing? This will flow only during the duty period, right? That is, your gate pulse is something like this. So your current will also be according to this, right? So your current will be 1.918 during this period, 0 during this period, 1.918 during this period, 0 during this period, and so on, right? So your total time is 10 microsecond and this was 8 microsecond. Okay. So you understand that for 8 microsecond it is 1.918 and then it is 0. So what is the IRMS? IRMS will be what? So you can go through the basic definition. That is, your RMS current is actually root mean square, right? So root of 1 by t integral 0 to t I square t dt. Okay. So what will be this value? Root over 1 by t. 1 by t is total time period, 1 by 10 micro, and then integral I square t, right? So my I is a constant 1.918. So into 1.918 square into the time, right? That is 8 micro. So what will be this particular value? So square into 8 by 10.
The total time is 20 micro, I think.
Yeah, fine. Thank you. It is 20. Yeah, right. It is 50 kilohertz, right? Thanks for clarifying. Yeah. So it will be 20 micro. So 1.918 square into 8 by 20. Root answer. So 1.213. 1.213 amperes. So this is your IRMS. So once you obtain your IRMS, you can always find out what is your conduction loss, right? So conduction loss will be I square R, I square RMS into RDS on. Another shortcut. So this is by definition, right? So this is by definition, or since this is a square wave, this is a square wave, right? It's a square and then 0, right? So IRMS can be directly written as something like your capital I, or let me call this as capital I. It can be written as capital I into root over D. Okay. So if you do by this formula also, you will end up with same answer, 1.213 amperes. Okay. So what is the conduction loss? Conduction loss will be I square R. I square RDS on. I RMS square RDS on. So 1.213 square into RDS on is 0.85. So this turns out to be around 1.25 watts. Okay, so this is how you compute your conduction loss. Right. So, oh, it vanished. Okay, so anyway, you understood, right? So P conduction is 1.25 watt, right? This is simply I square R. And how do you compute your switching losses? Switching loss you might have learned. P switching is equal to 1 by 6 into V into I into TR plus TF. If you have any doubt as to how we got this formula, you can ask me right now, but I think it is well explained by Professor Umanand in his video lectures. So it is actually 1 by 6 into V into I into TR plus TF. So this will be the energy, right? That is V into I into time. So this is the energy. Multiplied by your switching frequency will give you the actual power loss. Correct? Because power is basically energy by time. So this is your energy. So energy into frequency is power. Okay. So what is this value? 1 by 6 into what is your V? V is 40 volt because the MOSFET will essentially block 40 volt when it is in off state. So it is 1 by 6 into 40 into capital I we computed is 1.918. 1.918 into TR plus TF, right? So 23 nano plus 20 nano 10 power minus 9 into Fs. Fs is 50 kilohertz. 50 into 10 power 3. So how much does it turn out to be? 40 into 1.918 into 43 into T by 6. So 14 by 6 into 1.918 into 43 into 15 into 10 power minus 9. So it turns out to be around 27.49 millijoules. Okay. So this multiplied by your switching frequency will give you, I'm sorry. So this, I'm sorry. So this turns out to be 27.49 milliwatts roughly. Okay. So this plus conduction loss will give you the total loss. Okay. Right. So conduction loss was 1.251 and your TR and TF were 20 nanoseconds. So it is computed to be 0.0287 watt. We computed it as, yeah, almost same, 27.49 milliwatts. So your total loss, P total, will be P conduction loss plus P switching loss. So 1.25 plus 27.49 milliwatt is 0.027 watts, right? So it will be roughly, yeah. So it will be roughly 1.277 watts. Okay. So I think this is a pretty simple problem. Yeah, 1.28 watts. So any doubts over here in this problem? We just computed what is the conduction loss and switching loss. Okay, when the device is on, you just find out what is the conduction loss, that is I square RMS into R. You know how to find the RMS current, right? By basic definition also you can find, or as I told, IRMS can be written if it is a square wave. If it is kind of a square wave, you can write it as capital I into root over D. So D is 0.4 and capital I is 1.918. Okay. So by that also you can calculate IRMS, and I square RMS into R, it will give you your conduction loss. P conduction is equal to I square RMS into RDS on. Okay. So that's your conduction loss. And switching loss is 1 by 6 into V into I into TR plus TF into FS. So why is it 1 by 6? Because during each transition of TR and T, each transition of rise time and fall time, you will see that current or let's say the voltage will drop from VDD to 0, and simultaneously the current will increase from 0 to capital I. So current increases from 0 to capital I, and voltage will fall from VDD to 0. So, and this will happen during the TR interval. Similarly, vice versa happens during the TF interval. So if you integrate it, or if you find out the area under it, that is, if you do the power calculation, right? So you know that the energy will be integral V of t, I of t, dt. Okay. So if you integrate it, you will get the energy. The formula or will turn out to be something like this: 1/6 into V into I into TR plus TF. If you do the integration, right? So your voltage expression, this is your V and this is your I, right? So your voltage is basically a straight line, right? So you just write the line equation of your voltage, write the line equation of your current, and you multiply both of them, right? So you will get what is the energy. That will be something like this. Okay. We just directly employed the formula, but I guess you went through the derivation in the lecture slides. Right. So we will move ahead with the next question. Referring to the previous question, with junction temperature Tj of 100 degrees Celsius, ambient temperature of 30 degrees Celsius, for the maximum value of junction to case thermal resistance, find out the value of case to ambient thermal resistance. Okay. So in the previous question, that is IRF 840, what is the power loss that we obtained? So 1.277 watts. So this is what we obtained as the power loss. They are telling that Tj, I'm sorry. So they are telling that Tj is kept at 100 degrees C. Okay. And Ta is 30 degrees C. So now it's a pretty simple question. For the maximum value of junction to case, find the case to ambient. So you know that if you see the thermal chain of the device, you know that there is your Tj, right? And then you have a thermal resistance between the junction to case R theta, junction to case. So you come to Tc, that is the case. And from that you have case to ambient. If you don't have any if you don't have any heat sink, from case it is taken out to the ambient directly, right? So this is your Ta and this will be R theta C to A, case to ambient. Find out the value of case to ambient. So he's asking us what is R theta Ca. So if we go back to the data sheet, you can find out what is R theta Jc, right? R theta Jc is available in the data sheet. So let's go over there once again. Yeah. So R theta, yeah, you can see over here, R theta J to junction to case, maximum junction to case is 1 degree per watt. Okay. So maximum junction to case is 1 degree per watt, 1 degree per watt. Okay. So that is your junction to case. From this, you can find out what is R theta Ca, right? So just write the KVL kind of an expression. Tj is equal to what? Sorry. So Tj is equal to Ta plus P loss into R theta Jc plus R theta Ca, right? Because P loss is kind of the current that is going, right? So this is your P. Okay. Yeah. So P loss is going. So Tj is equal to what? Ta plus P loss into P loss into R theta Jc plus R theta Ca. So this is the drop that occurs through the thermal resistances. So from this you can find out what is R theta Ca, right? So just substitute the values, you will be getting what is R theta Ca. Okay. So Tj is 100 minus 30 is 70 divided by 1.277, right, minus 1 degree per watt. Yeah, so it's around 53 degree per watt, or 53.82 degree per watt is what we are getting. Okay, this is just from the thermal chain of the device. Okay, and R theta Jc is available from data sheet. Okay, yeah, so this is 53.8 degree per watt. Okay. So in this question, did you guys have any problem? I think this is a very good question that includes both um, your conduction loss as well as your switching loss, and also integrates your thermal. Yeah. So what is 8 microseconds? So 8 microseconds was the on time. Okay. So we'll go back to the question. See, they are giving that it is operating at 50 kilohertz with zero point 0.4 duty ratio. So it means that 50 kilohertz refers to 20 microseconds. And this is the total switching period, right? So total period. And zero point 0.4 duty ratio is the on time of the device for the duration for which the device is conducting current. So zero point 0.4 duty ratio means how much time is this? 0.4% or 40 percentage of your total time, or zero point 0.4. So zero point 0.4 into 20 micro, it is 8 microsecond. That is why we considered this period to be 8 microsecond, or this is the on period to be 8 microsecond, and we use it to compute what is the IRMS, right? Because I, or capital I, will be 1.918 when your device is on. So when the device is on, current will flow, right? I will flow. So I will flow only for 8 microsecond and 0 for the rest of the period. 8, and for again 8 microsecond it will flow, and 0 for the rest of the period. So IRMS is computed accordingly using that 8 microsecond criteria. Okay. So yeah, so this is where the 8 microsecond came from. Were you able to understand? Yeah. Okay, so if you don't have anything, we can go ahead to the next question, right? Um, where is, yeah, so here it is. A MOSFET is being operated in two different conditions, M1 and M2. Okay. Find out the ratio of drain current in these two conditions if the MOSFET has the gate threshold voltage of 3 volt. So V threshold is V threshold for both of them is 3 volt. So yeah, just excuse me for a second. Hmm. Yeah, so sorry for that. Um, so yeah, so in this question, the threshold voltage is specified to be 3 volts. Okay. The gate source voltage of M1 and M2 are 6 volts and 5 volts respectively. Assume the drain to source voltage of M1 and M2 are 4 volts and 3 volts respectively. Find out the ratio of the drain currents. Okay. So just jot down whatever is given. So VGS1 is 6 volt. VGS2 is 5 volt. Um, yeah. So VGS1 is 6 volt. VGS2 is 5 volt, right? And assume the drain to source voltage of M1 and M2 are 4 volt and 3 volt. So VDS1 is 4 volt. VDS2 is 3 volt. Okay. So find out the drain current. So first of all, we need to find out in which region the MOSFET is operating, right? So because depending on which region it is operating, the current can change. If it is in the cutoff region, current is 0. If it is in the saturation region, it's a controlled current source. And if it is in the ohmic region, it is just a resistor, right? So we just need to determine in which region it is operating. So you know that if the MOSFET is on, VDS being more than VGS minus V threshold, it will be in the active region. Okay, and it is a voltage controlled current source, right? It's a voltage controlled current source. Okay, so what is its value if it's voltage controlled current source? I channel will be Gm times VGS minus VTHD whole square. Okay, so this is if it is in the active region, and if your VDS is less than VGS minus V threshold, then it is in the ohmic region and it is just a resistor, right? Okay, so can you identify in which region the devices are operating? So device number one, you see VDS, is it more than VGS minus V threshold? VGS is 6 volt and V threshold is 3 volt. So your VDS is 4 volt. So 4 is more than 6 minus 3. So it is in the active region. And similarly about device 2, VDS is 3 volt and VGS minus V threshold is what? 5 minus 3. So 3 is more than 5 minus 3. So this is also in the active region. Therefore, currents of M1 and M2 are dictated by this particular expression, that is I channel is equal to Gm into VGS minus VTHD whole square, right? We just identified the region of operation. Now that we know this, we can find out the ratio, right? Right? So your I1 by I2, that is what they ask, right? Yeah. So I1 by I2 will be what? Gm into VGS minus VTH1 the whole square divided by Gm into VGS2 minus VTH2 the whole square, right? So Gm get cancelled. Assuming that Gm's are same, they have not given anything about that, but we will assume that Gm is same. So what is the ratio? VGS minus V threshold, 6 minus 3 the whole square divided by VGS2 is 5. So 5 minus 3 the whole square. So 6 minus 3 is 3, 3 square is 9 divided by 5 minus 3 is 2, 2 square is 4. Okay, 2.25. Okay, it's a very simple question. Just identify the region of operation and apply the formula that you are aware of. Okay, yeah, so that is what we have done, and again we obtained 2.25. Okay. Okay, so we will move over to the next question. Two MOSFETs are connected in parallel, similar to figure shown below. Okay, carry a current of 20 amperes. The drain to source voltage of Q1 is 2.5 volt and Q2 is 3 volt. Okay, so determine the percentage difference in current sharing if the current sharing series resistances are 0.3 ohms and 0.2 ohms. Okay. So this again a simple problem, just formed by others. It can be solved by first principles that we are aware of. So IT is 20 amperes, okay, and Q1 is 2.5 volt and Q2 is 3 volt, okay, and RE1 is also given as 0.3 ohm and RE2 is 0.2 ohm, okay. Okay. Right. So determine the percentage difference in current sharing. So basically we will find out what is IE1 and IE2. Okay. And find out the ratio, and from that we can find out the difference in current sharing. Right. Okay. So I will make use of this figure over here. So ID1 plus ID2, you know by KCL that ID1 plus ID2, ID1 plus ID2 is equal to IT, that is 20 amperes, right? And you also know that since both of them are in parallel, voltages will be same, right? The voltage over across Q2 and RE2 will be equal to voltage across Q1 and RE1, right? That is VQ2 plus IE2 RE2 is equal to VQ1 plus IE1 RE1, because they are in parallel, right? So I think it is obvious, right? So you know that VQ2 is how much? VQ2 is 3 plus, you don't know what is IE2, into RE2 is zero point 0.2 ohms is equal to VQ1 is 2.5 plus IE1 into VE1 is how much? Into RE1 is 0.3 volts, 0.3 ohm. Okay, so this is another expression, right? So this is one expression. Other expression is I1 plus I2 is equal to 20, right? So from this you can understand, right? So these are just two expressions with two unknowns, two linear expressions with two unknowns. So you can easily solve it, right? You understood, right? Because they are in parallel, we are just equating the voltages. So the voltage from this point to this point, okay? We are just equating the voltages. And the other expression is that we have a KCL over here, right? ID1 plus ID2 is 20 amps IT. So we have two expressions, two linear expressions with two unknowns. They can be solved easily, right? So, okay. So in the interest of time, I'm not going through the solving part, but you can understand that simply these are just two different expressions, right? So these two expressions need to be solved. Okay. So if you solve it, you will obtain what is ID1 and you will obtain what is ID2. Turns out it is 9 amperes and 11 amperes. So the difference percentage is what? 11 minus 9, 2 divided by the total current, right? That is difference is what? ID2 minus ID1 divided by total current into 100. Okay. Okay. So before we go on to the next question, any doubt? I'll just perhaps show this particular question once again. Just it is just a parallel connection of two devices. You need not worry that they have not given the values of VCC or RC, because all other relevant information is over here. So the MOSFET drops are given, the resistances are given, and the current is also given, total current. You can just find out the individual currents by applying KCL. That is I1 plus I2 is 20 amps. That is one expression. And since the devices are in parallel, you just equate, seeing the figure, you just equate the voltages in both the legs. So you get two expressions with two unknowns, two linear expressions. Just you need to solve it, obtain what is I1 and I2. From that, you can get the difference percentage, right? Because that is what is asked. Find out the percentage, find out the percentage difference in current sharing. So I1 minus I2 or I2 minus I1 divided by the total current into 100. Okay. Yeah. That is 10%. Okay. So, right. Okay. So we will go on to the next question. Which of the following options would provide the exact following characteristics? So you want you positive voltage blocking and positive current conduction and negative current conduction. Okay, so this is the device, positive voltage blocking and positive current conduction and negative current conduction is what you want. So from the given options, we can just easily eliminate, right? So consider example A. Can it block positive voltage? Yes, it can block positive voltage, right? If you don't give any gate pulse to this particular BJT, if you don't give any base current to this particular BJT, this BJT will not conduct. It can block positive voltage, right? So it can block positive voltage, positive voltage. It can conduct current from A to B, right? It can conduct current from A to B, and it can also conduct current from B to A. So yes, so A is one potential answer. And what about B? This is just a MOSFET, right? So MOSFET, you know that it can conduct bidirectional current and it can only block voltage from A to B. So yes, so it can block positive voltage and conduct bidirectional current. And what about this? It can conduct current from A to B. It can conduct current from B to A through this diode, and it can also block positive voltage from A to B if you don't give any gate pulse to this IGBT, right? This is simply an IGBT. So yes, C is a potential answer. Okay. And what about D? It cannot block positive voltage, right? Positive voltage cannot be blocked because this diode will start conducting. So D is not an answer. Okay. So what about A? It can of course conduct bidirectional current, but point is it can also block negative voltage, right? It can block voltage something like this. This is also possible. So this is a bidirectional switch. So A is not potentially a solution, right? Because it can block bidirectional voltage. So the options are B and C. That is, B is essentially a MOSFET, and this is basically an IGBT. Okay. Okay. So which of the following configurations is a 4-quadrant device? So 4-quadrant device as in like it should be able to block bidirectional voltage and conduct bidirectional current. So V I minus V minus I. Okay. So you just eliminate from here. So this device over here, can it block bidirectional voltage? No, it cannot block reverse voltage, right? So if you apply voltage from A to B, positive voltage from A to B, this diode will start conducting. Okay, diode will start conducting. And if you apply negative voltage from B to A, this diode will start conducting. So obviously, this is not the answer. It's not a 4-quadrant device. And what about this? We just saw this device in the previous question. It can block positive voltage. It can block positive voltage from A to B. It can conduct positive current from A to B. And it can conduct negative current from B to A. And it can block negative voltage from B to A. Okay. By using these BJTs as the controlling devices, and you have series diodes. Okay. So this is of course a 4-quadrant device. Okay. And what about this particular device? So can it conduct unidirectional? It can conduct current in this direction, right? And it can conduct current in the opposite direction as well. That is through this it can conduct. So it can conduct current in both directions, but can it block voltage in both directions? So you apply a positive voltage over here. This diode cannot block. So, but this BJT can block, right? So it can block positive voltage. And can it block negative voltage? You apply a positive over here. So what happens is obviously you get a positive here and negative here. Yeah. So it can block bidirectional voltage and it can conduct bidirectional current. So simply you apply positive voltage across A to B, negative voltage across A to B, positive current and negative current. You find out potential path for blocking and conducting. You will get the answer. So yeah, B and C can be bidirectional devices. And what about D? D can conduct bidirectional current, of course, right? And of course, since there are no antiparallel diodes, it can block positive voltage and negative voltage as well. So yeah, so the option is B, C, and D. Okay. Again, as I told, just apply positive voltage apply negative voltage, apply positive current, and apply negative current, and try to see the potential path for conduction. Okay, so that should give you the answer. Okay, so this is another simple question. Which of the following switches possess bidirectional current carrying capability? Diac, triac, SCR, IGBT, and MOSFET. So you know that MOSFET can conduct bidirectional current. We just saw it, right? So by this and by this, IGBT cannot conduct bidirectional current. Okay, unless you externally put an antiparallel diode, it cannot conduct, right? You have to have this antiparallel diode, only then it can conduct. So IGBT cannot, SCR cannot conduct bidirectional current, right? It can only conduct current in one direction. So, but triac and diac can conduct current in both directions. Okay. Why? Triac is basically an antiparallel connection of SCR, right? So you can have current conduction in both directions. Okay. So triac is basically an antiparallel connection of SCR. So it makes it a four quadrant device. Four quadrant device. Okay. Yeah. Okay. So again, we will go back to numerical problems. So, but till this point, you guys have any doubts? So when you will upload this video, I will upload this by tomorrow probably. It means continuous flow of current. Yes, they can. So it means point is, can it conduct current in both directions? Okay, so it can be continuous, it can be sinusoidal or whatever it is. Can it conduct current in either direction? Diode cannot conduct current from cathode to anode, right? So similar to that, the question is there. Can it conduct current in both directions? Okay. Okay. So we will try to cover as many numerical problems as possible. A MOSFET has a gate to source capacitance of 1 nanofarad, right? So gate to source capacitance, or CGS, 1 nanofarad. The gate current required to sustain the turn on of MOSFET is G dash amp dash milliamp if the gate source voltage is 12 volt. So VGS is 12 volt. What is the IG? First of all, right, as we were talking earlier, a MOSFET is something like this, right? You have a capacitance over here, you have a capacitance over here, you have a capacitance over here. So CGS, CGD, CDS. And externally, what you do is you feed in R through a gate resistance, you give the pulse, right? So you understand that whatever you give over here, CGS is charged to that particular value, correct? So essentially in steady state, in an RC circuit, you understand that in steady state, current is equal to zero, right? So initially there will be current requirement to charge up this MOSFET, and slowly the current will decay to zero, right? The current will be something like, it will decay to zero. If you turn on at this particular point of time, it will decay to zero once the capacitor is charged. So to actually sustain the MOSFET, or to keep the MOSFET on, you really do not require any gate current. The gate current is zero. You don't require any gate current to sustain the turn on of the MOSFET. Just to turn on, you require some gate current, but to sustain the turn on of the MOSFET, you don't require any gate current. You just need a positive voltage over here. Okay, a voltage which is greater than V threshold. You just need that. You don't need to have a continuous gate current to make sure the MOSFET is on. Okay. Yeah. So the gate current will be zero, right? You don't need any current to sustain the turn on of the MOSFET. Okay. Uh, just give me a second. I will have some water. Yeah, so thanks for hanging around. We will proceed. So consider the circuit in the figure, which consists of an ideal MOSFET and an ideal diode. The gate source voltage applied to MOSFET is illustrated in the figure. Find the average voltage across A and B. So again, this is a problem that is similar to the one that we saw earlier, right? That is, there is a voltage source and MOSFET is turning on and turning off with a particular duty. Okay. Find the first question is find the average voltage across A and B. So when MOSFET is on, you understand that when MOSFET is on, the MOSFET, okay, so when MOSFET is on, the MOSFET essentially shorts A and B, right? So VAB will be equal to 0, correct? When MOSFET is on, A and B will be shorted, right? So MOSFET is on. And they have told that it's an ideal MOSFET, so there is no drop as such. Okay, so VAB is equal to 0. And when it is off, what will happen? What will be VAB? When MOSFET is off, you understand that there is 20 volt, then an ideal diode will be forward bias, then 1K, and then 2K and 2K in parallel. So 2K and 2K in parallel is again 1K. So 20 volt with the circuit will become something like 1K, and then there is 2K and 2K in parallel, so again 1K. So the voltage across this will be what? Voltage will be 10 volts, right? Just voltage division. So you understand that the voltage will be something like voltage is 0 when the MOSFET is on and 10 volts when the MOSFET is off. 0 when the MOSFET is on, 10 volt when the MOSFET is off. So the voltage is, or VAB will be something like 0, 10, 0, 10 and so on. So what is the average voltage? VAB average. What is the average voltage? Just find out the area, right? Area by time. So average is 1 by T integral 0 to T f of t dt. Correct? So 1 by Ts into area, right? So what is the area? Area is 10 into whatever is this period. This period is, you can understand it is 0.4 Ts, right? So it is basically 10 into 0.4, right? It is 4 volt. Understood? This is just when MOSFET is on and MOSFET is off, we just found out. Simple, right? Okay. Yeah. So again, it's the same thing. VAB will be something like this, right? Between 0.6 to Ts, it will be high 10 volts. So that's why the average will be 4 volts. Just the area, right? 1 by T integral 0 to T f of t dt, or 1 by T into area. Okay, area is this. Okay. Okay. So find the total conduction loss in the previous question only. Find the total conduction loss in the diode in question 15 if forward voltage drop of the diode is 0.6 volt. So now they are telling that, see, the diode has a drop of 0.6 volt. Okay. So diode is having a drop of 0.6 volt. Find the total conduction loss in the diode. So what is conduction loss of the diode? VD into ID average. This is something we saw when we are doing diode problems, right? So conduction loss will be VD into ID average. VD is 0.6. We need to find out what is ID average. So what will be ID average? What will be I when M is on? So when M is on, right? I will be V 20 minus 0.6, that is the voltage, divided by, when M is on, it's a short, right? So divided by 1K, correct? So it is roughly 19.4 milliamps. And when M is off, Then what happens? I will be 20 minus 0.6, that is the diode drop, divided by what is the equivalent resistance right now? So the circuit will be something like, and then when M is off, it will be 1K, this will be 1K, right? So 20 minus 0.6 divided by 2K, correct? So 19.4 divided by 2, roughly 9.7 milliamps. Okay, so this is how my I will change. So it will be 19.4 milliamps when the MOSFET is on, 9.7 when the MOSFET is off. Correct? You understand, right? So this is how my ID will be there. So if this is my ID, you understand that ID average is, as usual, just the area divided by time. That is 19.4 into 0.6 plus 9.7 into 0.4. Okay, TS will get cancelled, so I'm not writing it. So it will be simply 19.4 into 0.6. Yeah, okay. So anyway, the answers came. So yeah, so the ID average will be 15.52 milliamps. So from this you can compute that the conduction loss will be V into I, right? That is 0.6 volt is a drop into 15.52 milliamps. So this is the conduction loss. Okay, got it? Just we found out the current through the diode and just multiply by VD, you get conduction loss. Simple, right? This is the conduction loss of the diode. Okay, so continuing with the same question, what is the power delivered by the voltage source considering the diode drop? So what is the power delivered by voltage source? So power delivered by voltage source will be what? 20 volt is V into I, V into I average, right? So I average was 15.52 milliamps. So 20 into 15.52 milliamps, right? So 20 into 15.52 milliamp, that is 0.31 watt. Okay, again, this is a simple problem, right? So any doubt so far, I'll just check the chat box or else we can go ahead. Yeah. So I think this was a pretty simple problem just with KVL, and by using common sense, you know that whether when the switch is on, what is the equivalent circuit, when the switch is off, what is the equivalent circuit. Okay. Okay. So we'll move on with the next question. Consider the circuit in the figure below, which uses IRF 260 MOSFET for switching. Consider calculate the switching loss associated with the MOSFET for the given gate pulse. Okay. Consult the data sheet and use appropriate parameters wherever necessary. Switching frequency is 10 kilohertz. Again, it's a very similar question to the ones that we have seen previously, right? Again, it's the same. That is, we need to calculate the switching loss. Just the switching loss alone, not the conduction loss. Okay. So for switching loss, we need to find out what is TR and what is TF for this software. IRF 260 MPPF. So we'll just go to the internet. IRF 260 MPPF. Yeah. So you go over here and go down. You get what is TR and TF, right? So TR is 60 and TF is 48 nanoseconds. So 60 and 48 nanoseconds, right? So TR is 60 nanosecond and TF is 48 nanoseconds. Okay. Yeah. So TR is 60, TF is 48 nanosecond. Okay. So Then you need to find out, so this is a gate pulse, right? You need to find out what is the VDS across the MOSFET and I across the MOSFET. Only then you can find out what is the switching loss, correct? So when the MOSFET is on, right? So when the MOSFET is on, what is the voltage across the MOSFET? So you just let me take another slide over here. Right. Sorry. Okay. So you just need to find out what is the voltage that is being blocked by the MOSFET when it is on, and what is the current that's flowing through the MOSFET. Okay. So when the MOSFET is on, right? So that is when gate pulse is given. What will happen? The MOSFET is turned on, correct? And it would thus have an RDS resistance. So what is the RDS that's given in the data sheet? The RDS is given to be 0.04 ohms, correct? So this resistance will yeah. So this resistance will be equal to 0.04 ohms when it is turned on, and of course when it is turned off, it acts like an open circuit. So you just need to draw what is the equivalent circuit when the MOSFET is on and MOSFET is off. So when the MOSFET is on, you understand that it is 20 volt, 10 ohm, and then you have RDS on, correct? So RDS on is 0.04 ohm in parallel with another 10 ohm. And when the MOSFET is off, the equivalent circuit is 20 volt. This is 10 ohm, and you have just a 10 ohm resistor. Okay, the voltage is across this, right? The voltage across the MOSFET is this. This is your voltage across the MOSFET. So in both cases, what you compute what is V, right? You compute what is I. Okay, you compute what is I, and that's it, right? So that is how you get the answer. So in the interest of time, I'm not doing this, but you understand that it's a simple problem, right? You just need to draw the equivalent circuit in both intervals, find out what is V and I, and from that you can compute what is your switching loss. Okay. So yeah, so as I was telling, when a MOSFET is on, RDS on comes in parallel with this 10 ohm, right? So this RDS on will come in parallel with the 10 ohm. Okay. Compute what is the current in this case. So compute the current. That turns out to be 1.99 amperes. When the MOSFET is off, it blocks a voltage equal to 10 volt, right? Why? Because when the MOSFET is off, what will be the voltage across this? So 20 volts is the total voltage. It gets divided or split into two equal halves because of these 10 volt resistors. So the voltage will be 10. So the voltage is 10 volt. So the voltage is 10 volt and current is 1.99 amperes. From this, you compute that the switching losses 1 by 6 into VDD into ID into TR plus TF into FS. Okay. So your VDD is 10 volt. It is not 20 volt, mind you, right? Because the voltage being blocked by the MOSFET will be simply just 10 volt. Okay. Across this. So 10 volt and ID is 1.99 ampere. Why? Because it is RL is 10 ohm. This is 10 ohm in parallel with this RDS. Okay. TR and TF we know from the data sheet into FS by 6. Okay. So this is your switching loss. Okay. Okay. So the next part of the question is calculate the total conduction losses in the MOSFET. So what will be the conduction loss? Conduction loss will be, we have done it multiple times. I RMS square into RDS on, right? I RMS square into RDS on. So RDS on is given in the data sheet as 0.04, and we need to compute what is I RMS square. So what is the MOSFET current? When MOSFET is on, you compute what is the current, that is 1.99 ampere. When MOSFET is off, obviously the current is also 0. So it is basically 1.990, 1.990, and so on, right? So what is the IRMS of this? IRMS is basically, we wrote that RMS is basically what? Root over 1 by t, 0 to t, square of t dt. This is one. Or I also told that if it is a square wave, I can write it as capital I into root over d. Okay. So here it is 1.99 into d is 0.4 into root over d, right? So from this you compute that it is 1.99 into root over 0.4. So 1.282585. Okay, this is the RMS current. So from this you compute the conduction losses I RMS square into 0.04. So that is 63 milliwatt. Okay, IRMS square into RDS on. Okay, so just compute what is the IRMS and multiply by RDS on. Okay, so till this point you have any doubts? Okay. Okay, so we just saw this, and yeah, around 63 milliwatts, right? RDS on is given, so total conduction loss is simply I square RMS into R. Okay, so we will move on to the last question for the day. Which of the following has a transconductance curve in the second quadrant? Okay, so if they tell the transconductance curve in the second quadrant, you assume that which of the following will actually conduct, right? Which of the following will conduct in the second quadrant? So what do they mean by second quadrant? So you have V, you have I minus V and minus I. Okay. So they are asking which of the following will conduct over here. Okay. Is it BJT? Is it MOSFET, JFET, or IGBT? So I think by elimination itself, you would have guessed that the answer is JFET. We just discussed this about probably an hour back. Point is, a BJT will of course conduct in this quadrant, right? It can conduct positive current, it can block positive voltage, right? And how does it conduct? Even a BJT or a diode, how does it conduct? It will conduct with a particular drop, correct? And this is for a diode. And what about for MOSFETs? You know that you have elaborately studied about the curves as well. You have something like this. I mean, this is for an IGBT, and of course, you have something similar for a MOSFET as well. However, for a JFET, you will see that a JFET conducts normally, right? A JFET is normally on, right? So you need to apply a sufficient negative voltage to turn it off. Therefore, you can understand that it inherently has its conductance in the second quadrant. Okay, unlike these three devices. Okay. Yeah. Yeah. So it is a depletion type device. So it is normally on. That's why we tell that it is in the second quadrant. Okay. So till this point, any doubt so far, or we can close for the day with this. Okay. So any doubt so far, please do tell, or else we can close for the day. We have pretty much covered the questions that I had planned for the day. So if you don't have anything, we can just stop over here. I will stop my sharing. Let me see if there are questions that are missed out. Yeah. So I think we are done. Okay, just one more question I just saw right now. This is a very simple question. So I'll just share you. Yeah, so I think I missed out on this question. This pertains to this particular week's syllabus. Which of the following is a feature of MOSFET from the given options? MOSFET has bipolar voltage blocking, unipolar voltage blocking, bidirectional current, and unidirectional current. Of course, you know that it has unipolar voltage blocking capability, unipolar voltage blocking, and bidirectional current capability, right? Because MOSFET can operate here. It has positive voltage blocking, positive current conduction from drain to source, and negative current conduction from source to drain due to the body diode. Due to body diode, okay, it can block VDS and it can conduct IDS. Okay, yeah. So this is a very simple question, but yeah, I just got missed out. Okay, so I will share the PPT. It will be uploaded in the drive. I think I shared the in the previous week's chat link itself. I shared the um, link. So all the PPTs will be available and recording as well. So yeah, I will stop the sharing and yeah. So good night, everyone. Thanks everyone for attending, and we will meet again next week.